who will talk for us on a very gentle introduction to blow-ups and applications to geometry.
Thank you, Tanya. First of all, I'd like to thank the organizers for giving me the opportunity to speak here. So today I'm going to give a gentle introduction to blow-ups, which is a technique that has been used in geometric microlocal analysis probably since 40 years ago, and it's still going strong. And so this talk will be very gentle, so I apologize to all the experts in the audience for the first 55 minutes of triviality. All right, so my plan is as follows. The first part will be talking about definition. So what is a blow-up and why we're doing this. So motivation. And the second part, I'm going to present two toy examples. One is called eigenresolutions or eigenvalue resolution. And the second one is a 1D Fredholm operator. And the third part, if I still have time, I would like to present some application to uniformization problems, to singular uniformization problems. Including two types of problems. The first type is spherical conical matrix. So spherical with conical singularities. And the second type is hyperbolic matrix with cusps. Okay. Hopefully this writing is legible. All right. Okay, so let me start with the first part, what is blow-up. So for this part, I'm going to follow on some lecture notes of Richard Merrill's, which you can find on this address. And I believe Richard gave a mini course in 2008 MSRI program. And so part of that will be from that lecture notes. And if you want to know more about the technical details, then there are more lecture notes just on the same website. Okay, so let me start by talking about, well, first of all, let me say, why are we using this? So what's the goal? So a general goal is that we want to understand singularity. In the real sense, in the real sin infinity setting. Okay, so in the complex setting, well, if you have some algebraic geometry background, then you'll know that there is a Hironaka's famous singularity resolution theorem that's saying that if you keep resolving the singularity, at some point you'll have a smooth complex manifold. And so what we're doing, in some sense, is a real analog. And today, my goal is to talk about the following thing, which is the real resolution or real blow-up. More specifically, it's going to be real radial blow-up. Okay, I'd like to mention that even in the real case, the blow-ups can have several types. So this is one, and there's projective blow-up, and there's also parabolic blow-up, which I believe Julia will talk about tomorrow. But today I'm going to focus on this case. All right, so, well, let me talk about some motivation, that why we're doing this. So as I said, that the motivation is that, well, if we just have a smooth manifold or smooth geometry, and if the operators are just uniform, non-degenerate, then there's no use for this technique. However, singularities arrive naturally in our research and in all kinds of problems, and that's where this is useful. So I'm going to present the following three circumstances. So consider the following three circumstances. Okay, and I think I should use a different board for that. Okay, so the three things are interrelated, but they arriving from different places. So the first one is singular function. singular functions. So for example, consider the radial function in R3. So consider R equals to square root of x squared plus y squared plus z squared in R3. Okay, so this function is smooth everywhere except at 0. So this is singular at 0. Right, if you compute the derivative, you'll see that. And so that's the first thing we'll talk about. And the second type of circumstance that arises here is singular space or singular geometry. Okay, so for here, I'll give an example of a cone. So what do I mean by a cone? Well, I'm just going to talk a Euclidean cone. So C is given by the following set of points in R3, which given by x, y, z, such that z squared equals to x squared plus y squared. And I also only want the upper half cone, so z greater than or equal to 0. Okay, so this is my C. Okay. In R3, that's a cone. All right, so this cone, you can see that it has a manifold structure away from the tip point. If you're away from the tip point, then nearby there's nothing special. It's very smooth. However, at the tip there's a problem, and in particular, if you think about it, what are smooth functions? What are called smooth functions on the cone? There's not a natural definition. And if you just use the regular smooth functions in R3 and restrict to the cone here, you'll have problem. Okay, so that's why functions and spaces are related. Okay. So that's a space, and the tip already gives us a problem. And in particular, well, I can talk about metric on this. So I can restrict the usual Euclidean metric on this cone. Well, and then you can compute it. Then this is going to be a conical metric. And in particular, you can write it as, here. As G equals to dr squared plus, let me make sure, 1 over a half r squared d zeta squared. Okay, so basically if you compute dx squared plus dy squared plus dz squared and use the correct coordinates, meaning using this r here, and the theta is just this angular variable here, and then you'll see that this gives you the formula. Okay, and this half appears here basically tells you that this is not a flat piece. There's actually a singularity here. Okay, okay, so that's the metric G. And you can see that the metric has some singularity, which we'll show up more later. Okay, and the third type of singularity I want to talk about is singular vector field. And a related object is singular differential operators. Okay, so well, when I say singular vector fields, for example, if you think about those vector fields, x dx, y dy, and z dz, on R3. Again, those vector fields, well, we can say they're smooth, but they vanish at this, they degenerate at the central point, and there's a problem. And in more particular, you can recombine those together with the theta. You can recombine them, and you'll get the following vector field, which is rdr. Okay, so r is still the same r here, and this vector field is degenerate. And in particular, I want to write out the associated Laplacian, the Laplace-Beltrami operator associated to this metric. And you can compute it. The operator is given by the following. So that's the second example. Laplacian of G is given by the following. Which, let me write it carefully. 1 over r minus 1 over r squared of r dr squared plus d theta squared. There is a 2 here. Okay. So that one is just directly computing from this G here. All right. Now, what's happening here is you can see that this differential operator, you can see that it's in the algebra formed by those vector fields, which has singularities. In particular, well, d theta is fine. D theta is just harmless, but RDR has problem, and it shows up here. Okay, so that's in particular. Okay, let me write it here. In particular, in our language, this is in r to the minus 2 differential, second order differential operator, but in the E sense. Okay. All right. So if you don't know this, don't worry. I'm not going to use it for this talk. But what I'm just saying is that it's related by those vector fields. All right. So correct. Right. I should also say that. Yes. D theta is not harmless yet. Yeah. Okay. So, well, now let me talk about a way to resolve this problem. So those three cases basically are focused on this one single object. And I'm going to introduce so-called this blow-up or resolution that will help us to resolve this problem. Okay, this is the correct word. So in this case, we introduce a blow-up. Now let me introduce the notation here. So this it's blow-up of 0 inside R3. Okay. In particular, it's written as follows. So this is R3 is the original space, and use then 0. So this means that we're blowing up the set inside R3. And this locally, well, globally, this is really the same as R plus, well, okay, should say R greater than or equal to 0 cross S2. Okay, so I'll draw a picture, and soon you'll know what I mean. And there is a map to R3. All right, now let me explain all those notations, what I mean here. Okay, so, well, we have our R3 here. There's nothing. And the blow-up here is really simple in the sense all I'm doing is just introducing the polar coordinates near 0, at 0. And what's happening is that I'm going to replace the 0 point here by a sphere. And everything else stays the same. All right, and that's my picture. So this is a space R3 blowing up at 0. Okay, and more particular, what's happening here is just, well, if I consider the following coordinates here, which is given by r omega, then it's mapped to r times omega, and that gives me back a point in R3. Okay, that's all I'm doing. Okay, so, and this map is called blow-down map. All right, so, well, in this case, it's just like that. And now, well, let me talk a little bit about what's happening to the cone there. So, well, what we see on the cone is that originally, well, I have this cone here. It's like that. And then if we introduce this coordinate here, then what's happening is that this cone, this tip is blown up, and it intersects, and the tip becomes a circle that's right on the sphere. And in particular, you can write it out that, so restricting to the cone, what's happening is that we can do a similar blow-down map, which is C hat to C, which the C hat is really given by r greater than or equal to 0 times S1 to C, which is just given by r theta mapped to r theta. Okay, so nothing special. All right. Okay, now well, let me talk a little bit about why we're doing this. So you might want to say, okay, this is just introducing polar coordinates. Now what I want to convey in the end after this example is that it does help us to understand those singular objects here. So first of all, so this beta is called a blow-down map. and has the following, well, has a lot of properties, but in particular has the following two. The first one is that it is a diffeomorphism, outside 0. Meaning that if we look at this picture here, well, if we look at the map here, and if you take out 0 from R3, and you take out the pre-image of 0 here, which is the sphere, then what you see here is really diffeomorphism, because, well, if you take R omega to mapping to R omega, if R is not 0, then this map is just non-degenerate. Okay, so this is saying that this blow-up preserves information outside singularity. Okay, and the second saying is that it relates singular vector fields by the following, in the sense that those singular vector fields, this r dr, d theta, x dx, y dy, etc., those are lifts to be smooth on this new space, R3, blown up at 0. Okay, so, well, this is in the sense that, well, you need to define what are smooth vector fields on here, on this new space, which is a manifold with boundary. And those vector fields are all lifted to a special class of vector fields. And in fact, there is a correspondence that all those vector fields that are vanishing at 0 has a one-to-one correspondence to those vector fields in this new space, or in R3, vector fields that tangent to the, let me just write S2 on this R3, on this new space. Okay. So it's not so obvious, and especially if you haven't seen this computation, it's just it seems like it comes from nowhere. But please trust me that if you do the computation just by a simple change of variables or chain rules, you'll see that it does happen this way. And what's nice about it is that, in particular, we can talk about the following. So let me say, just write one last line here. In particular, this Laplacian becomes nice in the sense that it becomes elliptic, or uniformly elliptic. In this new space, on this new space. And of course, again, you will need to talk about what are uniformly elliptic. But here, well, if we talk about introduce a new class, then you will see that. And well, I won't be able to say too much, but there's a lot of analysis related to this. And in particular, by introducing those new coordinates, what we can say is that, well, we can talk about this parametrics, we can talk about its Fredholm properties, and we can talk about a lot of mapping properties. Okay, so that's why this is useful.
When you say tangent, you mean it does not vanish on this sphere?
Right, it doesn't vanish on the sphere, yeah. Mm-hmm. For this class, it doesn't. Right. Yeah. All right. So this is my example 0 that hopefully give you some idea that what are blow-ups doing in general. So in general, what we have is some singular geometry or a singular metric or a singular function, singular operators. And usually the singularity would dictate what kind of blow-up or resolution we should do on the space to do that, to resolve the singularity. And well, and in return, this blow-up will give us new information. And this will help in two ways. So I mentioned these two things already, but let me write it out. So the first thing is that the blow-down map is a diffeomorphism. And in particular, in the interior. So in particular, if we gain new understanding on this blown up space, then what's happening in the interior will immediately tell us what's happening in the original space away from the singularity. So that's a new understanding that we can get. And sometimes you can get, say, asymptotic expansion near this singularity, and that's also holds in the interior, which is the original space that we care about. So this diffeomorphism would preserve information inside. Okay. Now, the second part that will help us is that we have those new boundary phases. And in some cases, these are bubbles. Okay. So you might have seen this bubbling analysis in some other type of differential geometry. And usually what bubbling analysis will tell us is that there's some energy or some information that's encoded in this point. And if you bubble it up, you'll see it. So that means that those new boundary phases actually encodes new information. Code new information. Sometimes it tells us there's some energy that's hidden or that's pinched down to the singularity before. Okay, so those are the two things that those two things are related, and those are the two things that usually we try to use blow up to achieve. Okay, now let me say a little bit about how to do blow up. So, analytically, what we're really doing is just introduce polar coordinates. At least in this radial blow-up setting, that's all we're doing. But it can be more complicated and can be iterated. And you'll need to choose your coordinate carefully. But usually, it just means you introduce new functions and claim it's smooth. Okay. And geometrically, it's replacing some submanifold by its inward pointing spherical normal bundle, which is the front face. Okay. So for the audience, either you have seen this definition or you're freaked out by this definition. So I'm not going to write it out. Instead, I'm going to present two toy examples, which will show how we do blow up. All right. Any questions so far? All right. So the two toy examples I chose today, one is more geometric and one is more analytic. And hopefully this will give you some idea that why they're useful. So the first example. Example 1. So this is called eigenresolution. Eigenresolution of self-adjoint matrices. Okay. So let me present the setting first. So I have two sets. The first set is a space of all self-adjoint matrices, complex valued, and n by n. So Sn is given by all those matrices, with complex entry, such that x star is equal to x. Okay. So x star is just okay, let me just write it out. X star is just the usual. Okay, all right. So that's the first space. And now, we all know that if it's self-adjoint, that means that for each such self-adjoint matrix, there are n numbers, which are their eigenvalues. So they have n eigenvalues. And write it as lambda 1 less than equal to lambda 2 less than equal to less than equal to lambda n. And they're all real numbers because it's self-adjoint. Okay, so that's the first space. And the second space is I'll have a group that's acting on the space, which is a group of unitary matrices. So, unitary. which just means that U star U equals to identity. Okay, and we know that UN acts on Sn by conjugate. So that is following that for U in UN, X in Sn, U act on X. So I use a dot as an action. So that's just a U, X, U inverse. OK. Now, what am I doing with the space here? I should really keep one of these here. All right. So, well, first of all, this unitary group acts on X in such a way that the orbits are very easy to see. Okay. So if you take a self-adjoint matrix and look at its orbit, which means that if you take all the UN acts on X and see what it give us, well, this is just all such matrices. And it's really given by all those self-adjoint matrices such that they share the same eigenvalue. Y and X has the same eigenvalues. Okay, so I mean this is very easy to see. If you look at the action here, this is just mean that the only thing we're doing is to change the eigenvectors, but the eigenvalues will be preserved. But well, of course, you can see that all the y in the space here doesn't need to have the same eigenvector. Okay. And now I want to consider the following. I want to consider the isotropy group of an element X. So which this is defined to be those elements in UN such that U preserves X. Okay, so, well, first of all, if this X has all distinct eigenvalues, then the isotropy group is just a point. Okay, so if X has distinct eigenvalues, so lambda 1 less than lambda 2 less than lambda n, then this isotropy group of X is really just a point, just identity. And the reason is, well, if you act by UN, then this means that you change the eigenvectors. And all the eigenvectors are distinct, and there's no way you can do anything. Okay. And on the other hand, if the eigenvalues are grouped, meaning that there are clusters, if the eigenvalues really satisfy this, meaning that I have the first, say, I1 eigenvalues are the same, which I'll abuse my notation. I'll call them I1. And the second class is lambda 2, I2, and less than equal to lambda m equal to lambda n. So suppose it has some clusters which should satisfy some ik equals to n. Okay. Then what's happening here is that the isotropy group of X is really isomorphic to a bunch of small groups. Okay. Okay, so these are just something that's very classical. And we'll see in the end why I talked about this, because I want to consider the orbit space. Now, first of all, just from here, you can see that the multiplicity of the eigenvalues really matter, because it changes the isotropy group and the isotropy type changes. So in particular, these isotropy types are in one-to-one correspondence to the partition of n numbers. Basically, how you cluster those eigenvalues will tell you which group you are. Okay? And now the problem I want to consider is more analytic. That is, I want to study eigenfunctions and eigenvalues on the space. So the first problem we immediately see is that eigenvalues are not smooth on the space. Okay. Yeah.
Is iso of X, how can it be identity in the case of those separate and not sum of U1, product of U1s?
Oh, sorry. Yeah, that's bad. I did something wrong with the. Yeah, that's really bad. Okay. Yeah. Thank you for pointing it out. Yeah. I was thinking about something else. Yeah. All right. So, but you can see that it does matter. Like what the clustering of eigenvalues will tell you what's the clustering there. Okay. So the first thing is analytically, well, eigenvalues are not smooth, and in particular, it's singular when the multiplicity changes. So that is, if you're inside this area where the isotropy group is the same, in the sense that the clustering is the same, then what you see eventually is that the eigenvalues are actually smooth. They're varying smoothly. However, if we jump from one isotropy type to the other, well, this can happen. You move from one point to the other point, then this is where the eigenvalue becomes singular. And I'll give an example in a moment. And the second related question is I also want to study eigenvectors. Now, my question is that, so consider this following trivial bundle, which you can view as I take one element. Well, I take one element in the in the symmetric group in this as a symmetric matrix, and I take Cn. Then, of course, I have n of eigenvectors. So for each point, this bundle decomposes into n one-dimensional spaces. Now, unfortunately, this trivial bundle doesn't decompose globally. Okay, so this does not decompose into n one-dimension rank 1 bundles globally. And you'll see that the problem is very related to number 1 in the sense that first of all, there is non-uniqueness in decomposition exactly when there's multiplicity. And secondly, there is also smoothness question. And again, question is where the multiplicity change. Okay, so this is an analytic problem in the sense that I just want to understand this function which is defined on the space, but this function is not smooth. Now, how can I make it smooth? What I can do is I'm going to introduce more variables, which is blow up, and then I can make it smooth. So the result is the following. The result is that indeed one can resolve this so that everything becomes smooth. And it decomposes globally. So there's a theorem in 2015 that there is an eigenresolution, I call it S hat, such that the following is true, that first of all, eigenfunctions all lift up to be smooth functions on this new space. So eigenvalues are lifted to smooth functions on S hat. And secondly, there is a global decomposition that this trivial bundle S hat cross Cn decomposes into n bundles, and each of them is an eigenbundle. Meaning that if you take one point and pick one of the eigenvectors, then this eigenvectors will just be extended to nearby as well. Okay, to this global thing as well. Okay, so decompose globally. Okay, now I intend to give a proof for the simple case, because that's the case that you can immediately see that where this blow-up arises when n equals to 2. Because in this case, everything is explicit. You can just do computation to show it. Okay, so well, in this case, let's just write out everything. So first of all, the space of 2 by 2 symmetric self-adjoint matrices can be written as following. So it's written as T plus A11, C plus DI, C minus DI, T minus A11. where T, C, D, A11, they're all real functions. Okay. So this is the space of self-adjoint matrices. So it's very explicit. And T, as you can see, I'm going to use it as my trace, or two times the trace. So this is a space, and I'm going to identify it with R4 so that I can talk about coordinates. All right, now let me leave this here for now. And the next computation, okay, well, before I talk more about computation, let me say that this is identified to be RT cross S0 and S02, which is just saying that I'm going to take out this T because this trace is harmless, and this is a space of traceless self-adjoint operators. Self-adjoint matrices. Okay. All right. Now I'm just going to do the following computation immediately. So in this case, the two eigenvalues is written as T plus minus A11 squared plus C squared plus D squared. All right. So for this, you can just do it here. If you're bored, you can just do it. And the eigenvectors corresponding to those two eigenvalues are given by C plus DI plus minus A11 squared plus C squared plus D squared minus A11. Okay, so, well, those eigenvectors are in C2, as expected. Okay. All right, so, well, immediately from here, you can see the singularity, where it's singular. So it's only singular as origin, which is A11 equals to C equal to D equal to 1, 0. Right? So if it's so that's the function that I introduced in the beginning. All right. And the second thing is that for the eigenvectors, you can see that, well, if A11 equals to C equal to D equal to 0, those two eigenvectors are degenerate to 0 vectors. So that's also where the smoothness becomes a problem. All right, so that's immediately we can see that, and therefore I'm just going to do the same blow up that I did for the example 0, that introduce the following S hat, which is given by R3 blowing up at 0 cross RT. Okay, so that's the space. And it's just that simple. And here R3 just means that I'm taking the space of A11CD and blowing up a 0. All right. And once you resolve this, you can see that, well, this eigenvalues become smooth, and you can also check that those eigenvectors lift up to be globally decomposed. All right. And so that's it for proof of when n equals to 2. And when, well, of course, for higher n, it's more complicated. I should just mention that there is an iterative scheme here, iterated blow up, according to isotropy types. Okay, and that's more complicated. I'm not going to write it out here. But hopefully, I convince you that this kind of singular functions that I introduced in example 0 actually appears in real problems. And now let me say a little bit about why we're doing this, and also mention that why I talked about so much group actions there. So this case is a special case of a more general scheme of group action resolution. Given by Albin Merrells, saying that for any reasonable group action, you can keep resolving your space so that eventually what's happening is that in the new space, if you look at the space of orbits, it's going to be a smooth manifold with boundary. So in particular, what we see here is that the space under this UN action is a smooth manifold with boundary. Which originally, if you just look at the space of Sn acting by Un, you'll see that it's super singular. And in particular, the problem is exactly because you have all those isotropy types, and then you have a lot of singularities that's occurred by when you jump from different isotropy types to another. And in particular, well, for example, for this one here, if you look at S2, S hat 2 acting by U2, this is just given by R greater than equal to 0. And for this one, it's easy to see that, as I said, that the orbits are just given by eigenvalues. And here, by resolving this, what we're saying is that, well, you resolve the eigenvalue singularity at 0, and once you quotient it out, you get say the positive eigenvalue, and the 0 is still there. So 0 is where we solved our problem. Okay, so that's the first geometry example I want to present, and. Now let me talk about a more analytic example. Great, I still have some time. Okay, so toy example 2. So this is, I'm going to consider the following operator, which is a one-dimensional operator. It cannot be simpler. This is given by x times 1 minus x d by dx plus c. And this is acting on an interval 0, 1. Okay. So this is an operator acting on functions on the manifold with boundary, which has boundaries, and the boundary degenerations are exactly encoded here. Okay, and here this C is an arbitrary complex number. Okay, and I should also say that this is the simplest B operator you'll see. So, well, if you find this unfamiliar, you can do the following: change of variables, write S to be log of x over 1 minus x. Then this S is from 0 to 1. You can transfer it to negative infinity to minus plus infinity. And this operator is really just this d by ds plus c. So, cannot be even simpler. All right. So you might want to say that why do we write it in this seemingly more complicated form? Well, the reason is that this is a simple case that we can actually do that. In a lot of cases, when you have complicated boundaries, you can't really just do this, do this transform and transform it to something that's more familiar. And that's where the boundary problems actually appear. But of course, it's good to keep in mind that, especially for those B problems, there is this exponential change there that will go back to the regular variables and regular differential. All right, now let me talk a little bit about this operator, the mapping properties of this operator. Which again, in this case, it's nothing special, just d by ds plus c on the real line. So there are a few things that I want to mention. So first of all, it's the function space I want to act on is PC is acting from HB1, 0, 1 to LB1, LB2, well, the L2 space. If you haven't seen this B space before, again, remember that if I do my transformation back to this real line, what those two spaces really are just H1, H1 R to L2R. Okay, so nothing special. All right. Now, this itself, there's not much interesting things happening, and in particular, you can just compute everything like what's the kernel and what's the mapping properties, and the kernel is just, well, you can see that as exponential functions, and the index of this function of this operator is 0. Now, if I want to make it more interesting, I want to impose what kind of function space I want to work on, which means that I want to impose some kind of boundary restrictions. And that's where I'm going to use the space in particular, because it's very hard to write in that way. So I'm going to forget about this now. And so it actually acts on from x. So I'm going to impose some decay condition or growth condition on two sides. And this is acting on x to the alpha, 1 minus x to the beta, where alpha, beta are real numbers. OK, so this is also, you can check that it also maps this way. And the fact is that, that this operator is Fredholm if and only if that, let me make sure, alpha is not the negative, yes, negative real part of C, and beta is not the real part of C. Okay. Okay. So you can check that easily in the sense that all you can see is that the only danger is we have this potential function that's in the kernel, which is the exponential function, which translate to this case, it's just x alpha and 1 minus x to beta. And the danger is that if this is the case, then that means that you have something that's almost in the kernel, but not. And that's bad, and that means that you have some non-close range. But if you exclude those cases, that's just Fredholm. Okay. Now, well, one thing I want to really talk about here is that I want to talk about its inverse of parametrics. Or more general parametrics. And let me do some shameless self-advertisement for next week's mini course that I'm going to talk more about general cases where pseudo-differential operators are used to construct parametrics. But here, it's very easy. You can just write it out. And in particular, let me write out the inverse by the following. So again, if you go back to this S variable, this is just differential. So, well, what's the inverse? The inverse is integral. So the inverse is really just integration. And you have to choose which end to integrate. But that's if you satisfy that condition, there's no problem. You know which end to integrate. So in particular, we have the following, that this QC acting on F will give you a function. And that's given by 1 to x of x over 1 minus x to the c times x prime over 1 minus x prime to the minus c fx times dx prime over x prime d1 minus x prime. Okay. So this is just saying that for any function f, if I do this operation by integrating this, then what I get is a function that solves, well, okay, let me just write it out. It's just PC QCF is equal to f. Okay, that's what I'm doing. F of x prime. Thank you. Yes. All right. So this is really just a fancy way to write it in the 0, 1 coordinates. If you write it if you compose everything back to this d by ds, this is just integrating the usual way. Okay. All right. Now, well, I want to write it in this fancy way because I want to show that we can see some singularities forming up here. So that is, I can write it as the following, which is, I can write it as using an integration, using a Schwarz kernel approach. So I'm going to write it as kxx prime times fx prime times dx prime over 1 minus x prime. No, there's x prime here. Yes. Okay. So, well, this kx x prime is equal to, just let me copy it, it's minus x to the 1 minus x c 1 minus x prime c over x prime c. And there's an extra function, x prime minus x, which is a Heaviside function here. So, well, this just reflects that I'm integrating 0 to 1, so I have to keep this factor 1 to x there. I have to stop it somewhere. Okay. All right. So this is in a fancy way, well, this is the Schwartz kernel of this inverse of this operator. Okay, Schwartz kernel of key. Let's see. Okay, now let me quickly draw a picture. Ah, right. The measure I'm using is this B measure, so that's just the, in the usual space, I'm just going to use this ds, and ds transferred to this 0, 1 space as dx over x times 1 minus x. Yeah. So that's yeah. So that's why there's a natural correspondence there. Yeah. Okay. Now, well, this is Schwartz kernel, and it lives in the double space, and this is a picture. So this is x, and this is x prime, and this is from 0 to 1, 0 to 1, and let me also draw the diagonal here. Okay. So the reason I'm drawing those 5 things, there are 5 lines here, and those are the 5 lines exactly where this Schwartz kernel is singular. Okay, so they're 0 or where it's 0 or has a divided by 0 or has a Heaviside function there. Okay, so those are the singular places, and you can see that in all other places the singularity is very easy to understand because, for example, at this point you only have this one singularity. Okay. However, or at this point it's a product type singularity. Again, it's very easy to understand. So, well, I say that it's very easy to understand in the sense that for using a regular integration kernel, and if it's this type, it's easy to control that. However, at those 2 points, that's a problem. It's not a product type. You have 3 things coming in. At least intuitively, you can see that it looks different from this corner here, for example. And that's a problem in understanding this kernel. And the way to deal with that is to do the following, which is we'll blow up the 2 corners by introducing polar coordinates, which is basically just given by, in the space of x and x prime. And by blowing up those 2 polar coordinates, and in this picture, what you see is that I just replaced this point by a quarter circle. And what's happening here is that, well, this line is still there, but this line is lifted. And this line is now separated from these 2 dangerous boundaries here. So my singularities are here. Okay. So I no longer have this very dangerous corner here. And then and that's basically the simplest case of B operator and the B space, the resolution in the B space, and that will help us to understand the integration kernel. For more complicated operators, of course, you have more complicated space, but that's the gist. Okay. So hopefully this gives you some idea, this analytic example gives you some idea that where those things come from. All right, now I have exactly 5 minutes, as I promised. Let me talk a little bit about how we use those things in our research. Okay, so I'll be very vague. So let me focus on this the example. So application to geometry. Okay, so the first example is those conical metrics. I'm not going to give very accurate definitions. I'm just going to draw pictures. So yeah, question? The operator, which operator? The kxx, the integration, sorry, the parametrics? Yes, it's still singular. Yeah. You mean here it's singular? Or? Right. It still has singularity, but the singularity is nicer in the sense that if you approach here, you have a 0 that's a single type. In the sense like here, you can see that it's like x. In the xy plane, it's just x. It's not like x times y. Okay. Yeah. I mean, it still has a 0. Yeah. But it's a product type that you can treat. So, well, I'm just going to draw some pictures. So conical metrics are those, I should say constant curvature conical metrics on surfaces are such things that it's a smooth metric away from some punctures. And near those conical points, what you see is that it has a conical singularity, meaning asymptotically it's given by a cone. For example, I can take a spherical football. That's a conical metric. And another example you might feel more familiar, that is, I can take 4 pieces of flat triangles and glue them up. Now, not only glue them up, I'll have to smooth up those edges in the sense that I'll just, so that they smoothly transfer. So I don't see this edge, and I only see those points. Okay. So this is a big object that, and still, we don't know. A lot of things we still don't know. For example, even the existence of uniqueness in some cases we still don't know. So, and there's a lot of active research going on. And what I want to briefly mention here is that there is this so-called merging cone process, which again, I'm just going to draw pictures. That is, if you consider a family of metrics with this property that it all looks similar except at this one place where 2 cone points or a bunch of cone points are getting closer and closer. So this can happen for a lot of cases. And locally, if you're in the flat case, you can think about a piece of paper. So just take a piece of paper and cut it off like that, and take 2 pieces like that and again glue them so that those edges you don't see. And then you can take a similar piece of paper with the same 2 cone angles, but make this distance smaller. Okay, so that's still a surface. So locally it looks like that. And then you can make it even smaller and smaller, and eventually they merge. And you just get a cone. So instead of 2 cone points, you get 1 cone point. Okay, so that's a local version. And so this kind of process, if you look at the metric, you'll see that it's very singular. And in fact, there is a bubbling phenomenon here. So again, let me just write out. Let me just draw a picture quickly and then done. So what's happening in the end is that at this point, there should be a bubble coming out, and the 2 points should be like that. Okay, so there is a bubbling phenomenon that encodes information of this degeneration. And let me just mention that some works that I did with Riff Mattel, 17 to 19, that we use this language blow-up to understand this process. So this is a process that, so this process is let me just write smooth in a new blow-up space, in a resolved space, And moreover, this process would help us to understand, the deformation problem or the uniformization problem in the spherical case, to understand the uniformization, which is still partially open in the spherical case. And let me just mention one word that so in this process, what we really are doing is, again, just introducing polar coordinates, but in a more complicated sense. And this kind of bubbling in the geometry sense, well, you can see it from the geometry, but also analytically, it tells us that this bubble encodes information. But if you're away from the bubble, what we're seeing here is that, this process can be understood using these new coordinates, and this is a polyhomogeneous or smooth in quote unquote a process using those new coordinates. Okay, so I think I'll stop here. Thank you for your attention.
You mentioned when you were doing these that you could do this by sort of iterating your blowups, and then you get at the end just a manifold of boundaries?
Manifold corners.
Oh, okay.
Yes, right, yeah.
That was my question.
All right, yeah, sorry. I should say manifold with corners, yeah. I mean, the special case for n equals 2 is a manifold with boundary, but once you have higher order, it's a manifold with corners, yeah. Yeah. Yeah.
Here, the bubble encodes the way you approach the code, that's right?
Right. So here, locally, so in this flat case, it's not obvious. But if you're in a spherical case, you'll see that the bubble encodes at the limit. The limiting case is that all the curvature disappears. You just have a flat. You just have a flat surface with two conical points and with Euclidean ending in here. And analytically, you'll see that if you do this, if you do asymptotic expansion of this metric up to this point, then the leading term is indeed encoded by this flat conical metric on this bubble. So that's what I meant by encoding the information. Yeah.
Okay, before we thank the speaker again, I didn't write on my hand here, but I should have told you what the topic of the panel discussion is, which is to the job hunt at various levels, things you can help yourself, help your case going forward looking for a job. So that's the panel continuing at 4:30 here, and then again a reminder after the first talk in the morning at 10:30 the group photo. So if you have trouble getting up, maybe you can manage to get